Bismillahirrahmanirrahim. Welcome to the second lecture of this week 2. In the last lecture, we discussed solidification and the shrinkage during the casting process. And while discussing that solidification, we discussed Chauvinov's rule that is used to calculate the time required for solidification of the cast product. And that Chauvinov's rule plays a vital role in designing the riser. So we will start with a numerical problem which says a cylindrical riser must be designed for a sand casting mode. The sand casting itself is a steel rectangular plate with the dimensions 7.5 cm into 12.5 cm and 2 cm. Previous observations have indicated that the total solidification time for this casting is 1.6 minutes. The cylinder for the riser will have a diameter to height ratio equals to 1, means it will have equal diameter and height. Determine the dimension of the riser so that its time to solidify is 2 minutes. So we have two time for solidification. The first one is for the casting one and the second one is for the riser. As you can see here, the time for solidification of casting is lesser than the time to solidification for the riser. So let's write down the Chauvinov's rule first. What was this Chauvinov's rule? That was time required for solidification equals to mole constant into volume by surface area exponent n, where V was the volume of the cast product. You can say volume of the or mold cavity, and surface area A is the surface area of the mold cavity. So we'll start by calculating the volume of the cast product, that was equals to, as it is given in the statement, 7.5 into 12.5 into 2, and that makes up, if you use calculator for this one, 187.5 centimeter cube. For the surface area, what it says, the casting itself is a steel rectangular plate. The casting itself is a steel rectangular plate. So just draw a steel rectangular plate here. Okay, so it says let's say the longest side is 12.5, this side equals to 7.5 centimeter, and the thickness of 2 centimeter. Now to calculate the surface area, how many faces we have? The surface area of this top face, right, plus the surface area of this bottom face, we have it here at the bottom, and plus surface area of this face and this face on the left, and the surface area of this front face plus the surface area of the face at the back. So we'll start with the surface area of this top and the bottom face, that is equals to 12.5 centimeter into 7.5 centimeter, right? And because we have two faces, so we have 2 into 12.5 into 7.5, okay, plus the other face, that is this front face, this face, and the face at the back, this back face. So it is equals to 2 into 7.5, 2 into 7.5, and we have two faces, first face and second face at the back, that is equals 2 into this surface area, plus now we have the side faces, this one on the right and that one on the left, so that is equals to 2 into 12.5, 2.0 into 12.5, and because we have two faces on the right and one on the left, that is 2 times. So if we calculate this one, so the total surface area we will get, that is equals to 267.5 centimeter square. So we have two values, the surface area of our cast product and the volume of our cast product. Now the second thing we have, we need to calculate, we have the volume, we have surface area, we know the time for solidification for the cast is 1.6 minutes, so we can directly calculate the mole constant, right? So we can calculate the mole constant, Cm equals to TTS divided by V by A exponent n, so that would be equals to 1.6 divided by 187.5 divided by 267.5 exponent 2. So if we calculate using the calculator, we will get the answer equals to 3.26 minutes per centimeter square. This is the mole constant for this mole, right, for this mechanism. With these dimension and the time, the mole constant would be 3.26 minutes per centimeter square. Now we have the mole constant. What it say, what we need to determine the dimension of the riser of, so that its time to solidification is 2 minutes. So we will use the same mole constant for this one, right? And we have the time to solidification is 2 minutes, right? Because we are using the same mole constant because it is dealing with the same mole. So the Cm is the same, we have the time to solidification, and all you need to determine is the volume and the area of the riser. So let me erase these calculation off. So what it says, we have a cylindrical riser, so the volume of cylinder would be pi d square h by 4, and the surface area of the cylinder is equals to pi dh plus 2 pi d square by 4. And there's one condition that is given in this statement, that is it has d by h ratio equals to 1. it has d by h ratio equals to 1, means diameter is equals to height, or you can just diameter is equals to height. So you can just place the diameter equals to height, so we will have the volume equals to pi d cube by 4. Either take it in the height form, or we can just reduce it for the diameter. And same is the case with the area. We will have the area equals to pi d square plus 2 pi d square by 4, and that makes up 1.5 pi d square. Okay, so this is the volume and area for riser. Now you can use the Chauvinov's rule for the riser, that was equals to TTS by A exponent n, and TTS was equals to 2 minutes as given in the statement here, that was equals to 2 minutes, and the cm is equals to 3.26 as we calculated, into V by A we have pi d cube by 4 divided by 1.5 pi d square exponent 2. So you can just simply cancel out this one, and you can cancel out this one, you can simplify it. So we will have d by 6 square equals to into 3.2 equals to 2 minutes. So you can simplify this one for the d, so ultimately we will have the value of 4.7 centimeter. This is the diameter for the riser, and as we have d equals to h, so this will be the height of the riser as well, and using this you can simply calculate the volume of the riser as well as the surface area. So we have the dimension now. As you can see here, just use this value d by h for any of those, volume or the area. I will just erase this one. Let's put these values in the volume. So volume would be equals to pi into d cube. What was the value of d? 4.7 exponent 3 divided by 4, and that would be equals to 81.5 centimeter cube. That was for the riser, while the volume for the cast product was equals to 187.5 centimeter cube. That was for the cast product, and this is for the riser. So we can see the difference between them. That's approximately, the volume of the riser is only 44% of the volume of casting. So you can see here that the volume of the riser is only 44% of the volume of the casting, but still its time for solidification is higher than the time required for casting to solidify. So this is why we need to consider the shape such that the V by A ratio of the riser is higher than the V by A ratio of the casting, so that we can have the higher time required for solidification. Now we'll consider some exercise problems of our book. Let's start with problem number 1. It says a disc 40 cm in diameter and 5 cm thick is to be cast of pure aluminum. In an open mold casting operation, the melting temperature of aluminum is 60 degrees centigrade and the pouring temperature will be 800 degrees centigrade. Assume the amount of aluminum heated will be 5% more than what is needed to be filled the mold cavity. Compute the amount of heat that must be added to the metal to heat it to the pouring temperature. So we need to calculate the heat that is required to supply to achieve the pouring temperature of 800 degrees centigrade for this pure aluminum. So if we remember the formula that was required to calculate the heat supply to achieve the pouring temperature, that was equals to rho V, the density into volume, into specific heat in the solid state, and the difference between the pouring temperature and the melting point, plus heat of fusion, plus specific heat in the liquid state, and sorry, this one is, so if you remember the formula that is used to calculate the heat supplied to achieve the pouring temperature, that was equals to density into the volume times specific heat in the liquid state into the temperature difference that was between pouring temperature and the melting temperature, plus heat of fusion, plus specific heat in the solid state, and from melting temperature to the TINA, room temperature. Okay, so here H equals to, let's calculate the volume first. It says disc of 40 centimeter diameter and 5 centimeter thick. So the volume of disc is equals to ID square H by 4, and we have I into 40 square into 5 divided by 4, and that is equals to 6283.2 centimeter cube. But it says assume that the amount of aluminum heated will be 5% more than what is needed to fill the mold cavity. So the mold would be equal to this one, but we need to heat 5% more aluminum than what is required. So the volume that will be heated equals to, that would be 1.05 times of 6283.2. So that would be equals to 6597.3 centimeter cube. So this is the volume that will be heated. So we have the density of the aluminum equals to 2.70 grams per centimeter cube, whereas the specific heat equals to specific heat in the solid state equals to 0.88 centigrade, and specific heat in the liquid state would be equals to 0.21. So you can directly put the values in this formula. we have H equals to density into the volume that is to be heated. Then we have Cl, the pouring temperature is 800 degrees centigrade minus the melting temperature plus heat of fusion is given in the question, the statement, that is 389.3 plus 0.88 into 660 minus 25. So we can calculate this one using the calculator. We will have the total value of 190,82756 joules. Okay, this is the heat that is required to heat this volume of aluminium to achieve the pouring temperature of 800 degrees centigrade ideally. Now let's move on to the second numerical. It says a sufficient amount of pure copper is to be heated for casting a large plate in an open mold. Open mold, obviously, which is in direct contact with the atmosphere. The plate has dimensions, the length equals to 20 inches and the thickness equals to 3 inches and the width equals to 10 inches. Compute the amount of heat that must be added to the metal to heat it to a temperature of 2150 Fahrenheit. Assume that the amount of metal heated will be 10% more than what is needed to fill the mold cavity, and the properties of the metal is given here. Again, we will have the similar method. We will simply calculate the volume using the given data, and the volume that is to be heated is 10% more, that is equals to 1.10 into the V0. And then we will use this volume in the formula of heating. Okay, so this is how we can directly get the answer. We can move on towards the next numerical. It says during pouring into a sand mold, the molten metal can be poured into a down screw at a constant flow rate. During the time it takes to fill the mold. At the end of the pouring, the sprue is filled and there is negligible metal in the pouring cup. The sprue is 6 inches long and its cross-sectional area at the top is 0.8 inch square and at the base is 0.6 inch square. The cross-sectional area of the runner leading from the sprue also 6.6 inches square, and it is 8 inch long before leading into the mold cavity, whose volume is 65 inch cube. So you can just draw our general schematic. This is our pouring curve, then down sprue into the runner. This is our pouring curve, then down sprue into the runner. And this is our so it says we have a sprue with the area at the top is 0.8 inches square and area at the bottom is that is 0.8 inches square, and the area at this bottom is 0.6 inches square, and the total length of the sprue is 6 inches. So the total length of the sprue is 6 inches, and it says the cross-section area of the runner leading from the sprue was also 0.6. So this is also 0.6. This cross-section area is also 0.6, like this one. And the total length of the runner is 0.8. So we have the total length of the runner is equals to 8 inches, not 0.8, 8 inches. And it says the total volume of the mold cavity is 65-inch cube, and the volume of the riser located along the runner near the mold cavity is 25-inch cube. So we have 25-inch cube. So it says it takes a total of 3 seconds to fill the entire mold, including cavity, riser, runner, and sprue. This is more than the theoretical time required, indicating a loss of velocity due to friction in the sprue and the runner. Right? So the time 3 seconds is lesser than the theoretical time required because of some friction losses. Find theoretical velocity, flow rate at the base of the down sprue, and find the total volume of the mold, and also calculate the actual velocity and flow rate at the base of the sprue, and loss of head in the gaining system due to friction. So let's start with the section A of this one, where it says find the theoretical velocity and the flow rate at the base of the down sprue. So what was the formula for the flow velocity? That was V equals to under root 2GH, and it makes 2 into, because of inch per second system, so we will use 32.2 foot per second square into 12 to convert it to the inches into the height, and that is equals to 6 inches for the sprue under root. So if we calculate it, we will get the answer. It equals to 68.1 inch per second. That is our flow velocity. For the volumetric flow rate, we have flow rate equals to cross-sectional area into the velocity, and that would be equals to, we have cross-sectional area at the bottom of the down sprue is 0.6 into the flow velocity, that is 68.1. So it makes up flow rate of 40.8 inch cube per second. So this is the part A. Second one, we have in the part B, it asks the total volume of this cavity. So that would be equals to volume of the mold cavity, that is 65, plus volume of the riser plus volume of this runner, that is 0.6 into this 8 inches. So we'll have 0.6 into 8 inches plus volume of the down sprue. So we have 6 inches length, and you can take the average of 0.8 to 0.6 because it is 0.8 inches square at the top and 0.6 inches cross-sectional area at the bottom. So we will have 6 inches into 0.8 plus 0.6 divided by 2. So you'll have the answer, that is equals to, if we sum up all these, it makes up 99 inches square, inch cube. In the third section, it asks the actual velocity and the flow rate at the base of the sprue and the head loss. So to calculate the actual velocity at the base of the sprue and the head loss, we will have the formula that equals to So in the section C, it asks about calculating the actual velocity and the flow rate based on the actual time, that was 3 seconds, and as the statement says, it is more than the theoretical time. So as we know that the time required to fill the mold is equals to velocity by volume divided by the volumetric flow rate, and to calculate the actual volumetric flow rate we can have q equals to the velocity divided by the actual time. What was the velocity here? The volume here, the total volume was 99 inch cube divided by the time, that is 3. So we have 33 inch cube per second. That is the volumetric flow rate, actual volumetric flow rate. And same is the case with the actual velocity. We know that the volumetric flow rate equals to cross-sectional area into the velocity. So to calculate the actual velocity using this value, we will have velocity equals to 33 divided by 0.6 cross-sectional area. So that would be equals to 55 inch per second. Now the last section, D, the loss of head in the gearing system due to friction. So we'll calculate the velocity. We'll find out the loss of head using the using the formula of velocity, and that is equals to under root 2 gh. So we'll have 2 into 32.2 converted into inch per second square into h, and we are not taking the original head. We need to calculate the head for the time 3 seconds, and for that one we will take the velocity. We'll just calculate it here. So we will have velocity equals to 55, and that's exponent 0.5. So if we solve for this one, we will have 27.8 into h exponent 0.5 equals to 55. We will have h exponent 0.5 equals to 1.978, or h equals to 3.914 inches. So the loss in head, so the loss of head equals to 6 minus 3.914, and it's equals to 2.086 inches. So this is the end of this numerical. It has said that it has we have a mold cavity of 65 inch cube and the riser 25 inch cube, a down sprue with the length of 6 inches and has a cross-sectional area of 0.8 at the top and 0.6 at the bottom, and we have a runner with 0.6 cross-sectional area and 8 inches long, and more metal is poured in such a way that the molten metal is filled up to this level. It is not in the pouring cup. So what it says, it asks about the theoretical velocity and the volumetric flow rate based on the theoretical values of this head, and the volumetric flow rate based on this theoretical velocity. Then it asks about the total volume, that means the volume of metal in this mold cavity plus in the riser, in this runner, and the down sprue. So this is our total volume. Then it says it is actually taking 3 seconds to fill this complete cavity, and that is less than the theoretical value, and sorry, that is more than the theoretical value. So based on this, it asks about the actual velocity and the volumetric flow rate. So we took out the formula for time required to fill the mold, that is the equals to velocity divided by the volumetric flow rate. So we need to find out the volumetric flow rate, so we calculate the volumetric flow rate using the actual time, that was 3 seconds. And same is the case with the volumetric flow rate. And to calculate the loss of head, we calculated the velocity. We use a formula for flow velocity taking into consideration the actual head, and we find out the actual head based on the if our velocity is 55 inch per second. And from this we are able to calculate the loss in head, that is 2.086 inches. So there will be a drop of 2.80086 inches here. It will be somewhere around, you can 4.086 inches somewhere. So this is all for this lecture. Should you have any question, you will reach me at the Google Classroom. Assalamu alaikum.